This is the first recorded solution to one of the most famous and difficult math problems of ancient Greece. How do you build a cube that has exactly twice the volume of another cube? As pointless as it sounds, this was a defining question for mathematicians of the era, and the search for a solution led to some of the most important mathematical discoveries of ancient Greece. One legend says that this problem originated in the 4th century BC, when the Greek island of Delos was in political turmoil. Desperate for a resolution, the leaders of Delos turned to the oracle at Delphi for help. The oracle told them that their problems would be solved once they doubled the size of their altar to Apollo, which was in the shape of a perfect cube. The Delians didn't understand the oracle's answer, so they went to Plato, who told them that the oracle was suggesting that they should spend more time studying geometry to calm their political passions. But once the Delians set to work constructing their doubled cube, they quickly realized that this simple-sounding problem was much more complicated than it appeared. The difficulties all start with a single question. How do you decide what numbers are allowed in math? In the distant past, long before the Greeks, math was a tool for arithmetic, in service of things like trade and commerce. So doing arithmetic meant working with whole number values, like the number of cattle in a herd. But eventually, advanced civilizations, like the Egyptians and the Mesopotamians, brought fractions and ratios into the picture. Maybe we have 5.5 bags of wheat, or we want to use a ratio to talk about the relationship between two lengths. These ratios of whole numbers were powerful tools, and they could be used to calculate measurements to a high degree of accuracy. By the 6th century BC, the followers of Pythagoras showed that these ratios of whole numbers were capable of describing all kinds of natural phenomena, ranging from musical harmony to the timing of eclipses. But soon, it was shown that there existed naturally occurring lengths, such as the diagonal of a square, which could never be represented as a fraction of two integers. So math needed to expand its horizons to accommodate this new category of incommensurable magnitudes, which didn't follow the old rules. The Greeks didn't even call these things numbers anymore, because the measurements couldn't be expressed within their current number system. Instead, they were represented as lengths or magnitudes of lines. But this isn't about just drawing any random line you want and somehow doing math with it. For a line to be usable in mathematics, its magnitude needs to be rigorously controlled by a precise and consistent methodology. One approach that became the gold standard for thousands of years was straightedge and compass constructions. Using nothing but unmeasured straight lines formed by connecting 2 points, and circles with a given center and radius, it's possible to generate a universe of geometric objects. But from the beginning, the idea that these simple tools would be all that you need to build the foundation for all of mathematics was already too good to be true. Now, the way we think about numbers and magnitudes has changed dramatically since the time of the ancient Greeks. But something else that's changed is our relationship to privacy. Your internet provider can track every website you visit, and they could sell that browsing history to data brokers. That's where this video's sponsor comes in. CyberGhost VPN. By encrypting your connection, CyberGhost protects your sensitive information on any network. With over 38 million users worldwide, CyberGhost is one of the most trusted providers on the market, boasting a near-perfect rating on Trustpilot. CyberGhost encrypts your activity and reroutes it through secure servers in over 100 different countries, so you're protected from hackers, your ISP, and even CyberGhost itself. It also unlocks geo-restricted games and content from over 40 streaming platforms, and it can even reveal better deals when you're shopping online. CyberGhost works on all major devices and operating systems, and you can protect up to 7 devices at a time, so you can even share it with family and friends. Right now, you can get 84% off, plus 4 months free with the link in the description. And there's a 45-day money-back guarantee, so you have nothing to lose. Now, back to the video. Here's an example of the power of straightedge and compass in action. If you want to construct a square that has twice the area of another square, you might start by using a ruler and compass to construct the first square with an arbitrary side length. Let's give that length a value of 1. Then you take the diagonal of that square and you use it as the side length for the new, bigger square. Since the area of the first square was 1, then the area of this new square is exactly 2. So we can prove that this constructed length is the square root of 2, even though the magnitude can't be precisely written as a fraction. But ruler and compass constructions could model arithmetic operations too. Addition and subtraction are straightforward enough, but you can even model multiplication and division with the help of similar triangles. So therefore, any counting number and any fraction of counting numbers can be constructed with a ruler and a compass. In effect, these tools will become powerful mechanisms for doing what we now describe as number theory, as well as tools for creating geometric diagrams. Because along with the standard arithmetic operations, the ruler and compass have new powers too. By making clever use of the proportions in these similar triangles, the ruler and compass can construct the square root of any constructible number. You start with a length of 1, and then you add the length that you want to take the square root of to the end, like this. Next, you construct the circle whose diameter is the line that you just drew. Drawing a perpendicular from this point here gives the altitude of this right triangle. Because that altitude creates two smaller triangles which are similar to the original, they have all the same angles and ratios of their sides. This pair of lengths and this pair of lengths are proportional. And we can interpret this proportion to say that this middle length equals the square root of the product of the other two. It's what the Greeks called a mean proportional. Procedures like this eventually gave the Greeks a powerful geometric way to solve problems that today we'd use algebra for, like quadratic equations. During the time of Plato and the Delians, about a century before Euclid wrote his Elements, ruler and compass constructions would have already been in use, but different mathematicians would have had different criteria to decide what made a particular construction valid. Back on the island, the Delians still needed to construct the side length for their doubled cube for Apollo. But solving this problem was much harder than doubling the square. If you double the length of a single side, then you get a new shape which has twice the original volume, but it's not a cube anymore because the sides aren't equal. But doubling the length of all three sides multiplies the volume of the cube by 8. So doubling the volume while still keeping it a cube means we need to find some other multiple for the sides, bigger than 1 but smaller than 2. This value is the cubed root of 2. The Greeks had methods to approximate this value to arbitrary accuracy, so there's no question that an exact value must exist. But precisely constructing this ratio was much harder than it was to double the square by taking its diagonal to get the square root of 2. Unlike square roots, the cubed root doesn't emerge naturally from right triangles. But yet, maybe there's something about the method for constructing square roots that could lend insight into a way to work with cubed roots. About a generation before Plato and the Delians, a mathematician named Hippocrates of Chios made a discovery that would ultimately be crucial to solving the cube doubling problem. If the mean proportional gives you the square root of the product of two numbers, then two mean proportionals would give us a cubed root. The Greeks would have had a different approach here, but we can see how this works by using algebraic notation. Split this into two separate equations, then, after you cross-multiply, substitute x squared in for y in the second equation and solve to get your cubed root. Let's go back to the triangle we used earlier to construct square roots, but this time we'll look at the relationship between this middle-sized triangle and the biggest triangle in the figure. Once again, these sides form a mean proportional. But if we could somehow create a series of similar triangles with proportions that are linked in the same way, then we would have this relationship. And then, finding the cubed root of 2 would simply mean setting it up so that this line is twice as long as this one, and finding this length. But what method could we use to precisely generate a figure like this? Getting the 2-to-1 ratio we're looking for means setting up the sides and angles of this triangle in some precise way that we can't just measure out ahead of time. So, to help the Delians, Plato sent the problem to a few of the greatest mathematicians of the era, including Archytas, Eudoxus, and Menaechmus. The first one to come up with a solution was Archytas. His approach was so complicated and the origin for his idea so mysterious that even 20th century commentators were still raving about it. One said that Archytas must have had divine inspiration when he figured this out. Here's the basic idea. This intersection of a cylinder and a torus gives us this odd curve. And then if we generate a cone with an angle of 60 degrees oriented like this, we get the single point of intersection of all three right here. If you use modern tools to graph these figures in Cartesian coordinates and then solve for the intersection point with algebra, then sure enough, you'd see that the distance here along the xy plane is exactly the cubed root of 2. But how could Archytas have come up with any of this thousands of years before analytic geometry? What sort of rules of the game was he playing by, where he could apparently wave a magic wand to generate these complicated shapes out of nowhere, but yet somehow doubling the cube was a difficult research problem? The only surviving copy of Archytas' work comes from almost 900 years later, in a commentary on Archimedes by Eudoxus of Ascalon, so details were definitely lost. But if we look closely enough at the surviving text, we can see that there is a method to the madness. He keeps talking about what happens when two-dimensional shapes rotate and meet each other in different ways. While most of the individual lines and circles in his diagram are constructible with a ruler and compass, Archytas needed something else to fully solve this problem. Motion. By adding rotation in 3D space, he was able to get the answer that he needed. This motion can be represented mechanically by building a device with rods attached to tracks and hinges. A cylinder can be generated by a post which sticks out perpendicular to the ground and moves along this circular path. Similarly, the outline of a torus can be formed by another rod. This one spins like this to trace a circle, and then by rotating this part like it's attached to a hinging door, we can get the surface of our torus. Finally, we can form a cone by setting two rods at a specific angle to one another, and then keeping one of them anchored to the floor while we rotate the other like this. Since we used a ruler and compass to set our cone angle to 60 degrees, these lines, cutting through the circles, give us the 2-to-1 ratio that we're going to need for doubling the cube. When we move this entire contraption together by swinging the door, it looks like this. At a certain point, the three rods lock into place. This is the exact intersection point of our three surfaces. We know the diameter of a circle forms a right triangle with any point along its circumference. That fact, along with a few ancient Greek rules about proportions, allowed Archytas to show that this formation of right triangles is exactly the diagram we need to double the cube. The length of this part of the triangle right here is exactly equal to the cubed root of 2. Now, we can't say for sure whether Archytas actually built a mechanism like this with rods and hinges, or if he was thinking purely theoretically. But however he did do it, it's clear from the text that Archytas was using motion of some kind, and the evidence strongly suggests that his solution involved a mechanical device. Secondhand accounts say that Plato criticized Archytas and the other geometers for using mechanical means to double their cubes instead of using pure reason. Even though these days we often consider Plato's philosophy to be almost inseparable from Greek geometric reasoning, things weren't so simple back then. The technical mathematicians of the time, the ones who were actually writing theorems and proofs, didn't necessarily see eye to eye with the pronouncements of a philosopher like Plato, who called some of their ideas ridiculous. While the specific details about Archytas are a bit cloudy, we do know for sure that many Greek geometers were getting their hands dirty and using mechanical means to instantiate their math, despite the idealized notions of Plato, where mathematics is meant to exist in a separate universe of perfect forms. But in this time of experimentation and debate, there wasn't yet a clear consensus, even among mathematicians, about what methods should lead to a legitimate geometric construction. So Archytas' complicated solution involving three-dimensional motion was far from the last word. The next person to come up with a solution was Eudoxus. He was a student of Archytas before becoming one of the greatest mathematicians of his generation. Unfortunately, his solution has been lost forever. All we know is that it somehow involved curved lines. But we do have the next solution from one of his students, Menaechmus. Even though the Greeks didn't have algebra, their geometric understanding of proportions was strong enough to see that finding values that satisfy any two of these three relationships would allow us to solve our ratio for doubling the cube. So Menaechmus found a way to generate two-dimensional curves that represent these proportions, and then he used them to construct a new solution. The problem is that you can't draw these curves with a ruler and compass. The best you can do is to start to get a picture of what they'd look like if you were to construct individual points one by one. To represent what we would describe as y equals x squared, we can make this line our y and then use our method for constructing square roots to map points along the curve. In modern terms, this approach is like we're graphing points for the equivalent equation x equals the square root of y. For each point, using the ruler and compass to form a mean proportional means that the height of our triangle gives us the distance along this axis for our point which goes right here. Then, by taking different y values and constructing the square roots to find their associated x values, we can plot the shape of the curve. By taking two of these curves together, if we could somehow find their intersection point, then it would give us exactly the answer we're looking for, the cubed root of 2. It's believed that the Greeks knew how to make pointwise constructions like this, but they wouldn't have considered this method to be precise enough to give them the answer that they were really looking for. After all, if you can't already construct the cubed root of 2 using some other method, then you would have no way to use pointwise constructions to generate the correct intersection point. There's no straightforward way to construct a magnitude whose square root equals the cubed root of 2. So the best you could get would be an arbitrarily close estimate, which they already had. But somehow, Menaechmus realized something else. These curves, which we call parabolas, are in fact the shape that you get when you take a cone and slice it parallel to one of its sides, like this. But going from these pointwise constructions using similar triangles to slicing cones is a pretty big leap. How did he know that these two methods really lead to the exact same curve? Here's one way that he could have figured this out. Let's start by choosing some arbitrary point along this curve. At this point, we can also chop off the cone parallel to the floor to make a circle right here. We can use the circle to get our horizontal distance like so. The length of this segment connecting the diameter to the curve is like our x-coordinate. Somehow, we have to show that the distance along the curve here is proportional to the square of our x-coordinate. Let's start by forming that same mean proportional triangle that we've been using elsewhere. Once again, this is a circle and this line is a diameter, so this is a right triangle. Right away, we can see that the square of this length here is equal to the product of these two lengths. Let's call this length 1 like we did before. Now, we know that the length of a times 1 is always equal to the square of the length that we're calling x. But this part a isn't the length we're looking for. To make a parabola, we need to be able to say something about this length here. But luckily, the way that we've sliced the cone, the triangle formed by any point along the parabola will always have the same proportions. So the ratio between this length and this length never changes. In other words, the thing that we're calling our y value will always be a constant multiple of x squared. In fact, by cutting the cone in the right way, we can generate any parabola we want, because moving the original slice down or up like this stretches or compresses our parabola. Speaking algebraically, it changes the coefficient of the equation. But cutting cones isn't just for parabolas either. If we rotate the cutting plane like this, then we can form the other shapes from the same family of curves. This is an ellipse, which becomes a circle, and then this is a hyperbola. Together, these are known as the conic sections, and Menaechmus is credited with their discovery. In addition to his cube-doubling solution from the intersection of two parabolas, he's credited with another approach, using the intersection of a parabola and a hyperbola. Once you start thinking about these shapes in terms of slices of a cone, you realize that they show up everywhere. They're in everyday images, like the shape you see when you look at a circle from an angle, or the behavior of a conical beam of light when it shines on a flat surface. 2,000 years after Menaechmus, Johannes Kepler discovered that the very motion of the planets follow elliptical paths formed by these conic sections. But all of this still leaves us with a question. What good does it really do to know all this arcane stuff about cutting cones anyway? How does it help those poor Delians solve their cube doubling problem? Evidence from ancient Greece about whether and how they might have physically generated conic sections is slim, so there's still debate about this point. But Viktor Blåsjö argues that in all likelihood, Greek geometers would have again used mechanical tools just like they did elsewhere. We do know that hundreds of years later, Arabic mathematicians used devices called conic compasses. These were special compasses whose swivel points could be set in such a way that the tip of the pencil could generate the arc of a parabola, as well as a hyperbola or an ellipse. The compass naturally creates a cone pattern, so changing the angle that it makes with respect to the paper gives us these different curves. Leonardo da Vinci later made his own version of conic compasses, which illustrate this idea nicely. Given how closely related this mechanism is to the way the Greeks described their conic sections, it's plausible that they would have also used devices similar to these, even though the written evidence to support this is practically non-existent. In the centuries that followed, almost every great mathematician of ancient Greece had their own signature construction for doubling the cube. These constructions involved using various mechanical devices designed to construct two mean proportionals, to physically generate the cubed root of 2. But none of them ever quite reached the type of simplicity of action that made the straightedge and compass into the foundational arbiter of truth until well into the 17th century. But for the Greeks, it wasn't just about doubling cubes. They were similarly obsessed with two other related problems. Squaring the circle, which means constructing a square with exactly the same area as a given circle, and trisecting an angle, precisely splitting an arbitrary angle into 3 equal parts. But why did they go to such elaborate lengths to solve these simple-sounding problems anyway? Even though they couldn't prove it at the time, it's likely that the Greeks assumed that these problems were unsolvable with ruler and compass constructions. So each elaborate solution would have been designed to propose an alternate method. Because if the rules of construction with a ruler and compass don't apply, then the question is, what new set of rules are going to replace them to ensure that math is being done rigorously? It actually took until 1837 for Pierre Wansel to use techniques from Galois theory to finally prove that doubling the cube and trisecting an angle are impossible with the ruler and compass. And the proof that squaring the circle was impossible didn't come until even later, when Ferdinand von Lindemann finally proved in 1882 that pi is a transcendental number, which means it could never be the solution to a polynomial equation. So, whatever happened to those poor Delians? Accounts vary. Some versions of the story say that they were suffering from a plague rather than political turmoil. But who knows, maybe the plague caused the political turmoil. That kind of sounds familiar. In any case, the mathematicians' solution to the cube doubling problem didn't seem to solve the Delians' problems. The island was an intellectual and cultural center during the Hellenistic era, but eventually it declined, and today it's just a historical site with a population of 24. But if the Greeks' obsession with these pointless-sounding problems wasn't actually about practical application, then their real motivations would look pretty familiar to mathematicians today. Take a famous modern problem like the twin primes conjecture. It's the idea that there's an infinite number of pairs of prime numbers which are 2 units apart from each other. It sounds like a trivia question, but over 175 years since the problem was formalized in 1849, nobody's been able to prove it, even though there's been some major progress in recent decades. On the one hand, who cares if this turns out to be true? But on the other hand, the search for the proof for this simple-sounding problem has led mathematicians to discover new connections between wide-ranging branches of math. But this still doesn't explain why the Greeks were obsessed with finding so many different ways to solve these simple problems. So here's another way to look at it. Imagine that historians of the future are looking back at the 2020s. For some reason, most of the documentation has been lost and all that remains is a few scraps. These historians might look at computer engineers from the era and wonder, why were these guys so obsessed with making videos of Will Smith eating spaghetti? What was it about Will Smith or about spaghetti that was so important to them anyway? And if they really wanted a video of Will Smith eating spaghetti so badly, why didn't they just ask him for one? Why did they need to concoct this elaborate generative AI technology just to get videos of Will Smith eating spaghetti? Just like the cube doubling problem, the Will Smith eating spaghetti problem isn't the point of the technology that comes out of it. The problem itself is a functionally useless task, but it serves as a litmus test or a metric for the progress in the field. Both of these problems are catalysts for progress and showcases of the limits of the current tools. It's not a stretch to say that across history, the people who kept digging and digging at apparently pointless problems like these have been the ones to discover some of the universe's deepest truths.